Hello again, everyone. We are starting our third lesson now. In the previous session, we discussed the substitution method. Today, we are going to talk about trigonometric substitution. This is a fresh topic, and I'm sure we will master it together. Let's dive right in. All right, in the last session, we covered the substitution method. I mentioned that in some problems, products or quotients can't just be simplified. So what did we do? By using substitution, we were able to evaluate the integral. Today, we're going to delve into trigonometric substitution. This method is different from standard U substitution. In that method, we take an expression in terms of x and call it u. Now, in this method, we express x in terms of a new variable. There are three distinct cases. We're going to work through all three very thoroughly. The first case involves integrals containing the square root of a squared minus x squared. You might say, well, we used to handle something similar to this with arcsine. Yes, but we want to work on cases that the arcsine method simply doesn't solve. What does that mean exactly? It means you might not have the exact expression, the square root of a squared minus x squared, or even if you do, when you try U substitution, the derivative might not be there. However, you'll understand this clearly with examples. The rule states whenever you see the square root of a squared minus x squared, let x equal a sine theta. So, whenever you encounter the form square root of a squared minus x squared, we let x equal a sine theta. Now let's solve an example to see how this method works. Let's look at the first example. It is the integral of dx over the square root of 16 minus x squared, all cubed. Now, if it was simply 16 minus x squared without the power, you could solve this using arcsine. But here it has a power of 3, so we can't use arcsine. So, what do I do here? I use trigonometric substitution. Look, it has 16 minus x squared. This matches the form a squared minus x squared. So a is 4. I let x equal 4 sine theta. So x equals 4 sine theta. Now, what do we do? Since theta is introduced, we can't have both x and theta in the integral. So we will convert all x terms to theta. All right, how do we do this? We have x equals 4 sine theta. I'm going to differentiate both sides. What do we get? It is dx equals 4 cosine theta d theta. All right, now let's rewrite the entire integral. Remember, dx was in the numerator. So dx becomes 4 cosine theta d theta. Let's substitute that in. So the numerator is 4 cosine theta d theta. And the denominator, 4x, we use 4 sine theta. So we get 16 minus 16 sine squared theta, all cubed. Excellent. Now, I factor out 16, so I get 16 times 1 minus sine squared theta. And what is 1 minus sine squared theta? It becomes cosine squared theta. So under the radical, we have 16 cosine squared theta, all cubed. Okay? What is the square root of 16 cosine squared? It is 4 cosine theta, but remember, it is also cubed. So we get 4 cosine theta, all cubed. Now, what do we have in the numerator? In the numerator, we have 4 cosine theta. We cancel this with the denominator. So in the denominator, we are left with 4 cosine theta, all squared. Now, what is 4 squared? 16. I can move it outside the integral. So it becomes 1/16 of the integral of d theta over cosine squared theta. This looks familiar. The integral of the theta over cosine squared theta is tangent theta. So we found the solution in terms of theta. However, the original problem was in terms of x. So we have the answer, 1/16 tangent theta. However, we want the final answer in terms of x. Therefore, we must express tangent theta in terms of x. It is easy. Just recall your basic trigonometry. Let's see how. Remember, we let x equal 4 sine theta. What is sine theta it is x over 4. Do you remember the definition of sine? It is opposite over hypotenuse. So since sine theta is x over 4, the opposite side is x, and the hypotenuse is 4. By using the Pythagorean theorem, we find the adjacent side. So our triangle is complete. The opposite side is x, the adjacent side is the square root of 16 minus x squared, and the hypotenuse is 4. Now recall the definition of tangent, it is opposite over adjacent. So tangent theta is x over the square root of 16 minus x squared. So what was the answer? It was 1/16 tangent theta. Therefore, the final result is 1/16 times x over the square root of 16 minus x squared. This is a really fascinating technique, but it takes some practice to master. It might feel new at first, but I'm confident that with more practice, you'll get it. Now let's move on to the next example. Well, we said if we see a squared minus x squared, we let x equal a sine theta. Now, if we see a squared plus x squared, either under a radical or outside, this time we let x equal a tangent theta. Let's look at an example. The integral of dx over the square root of 9 plus x squared. We cannot solve this using ordinary substitution. If it has a radical, we can. If it didn't have a radical, we could. But this question has a radical, so what do? A squared is 9, so a is 3. That's right. We let x equal 3 tangent theta. From this point on, you can calculate the rest yourself. Keep the goal in mind. Pause for a moment and think, what is the objective? Don't get lost in the problem. We let x equal 3 tangent theta. Now, I want you to rewrite the integral so that no x remains. Everything must be expressed in terms of theta. Take a moment to try it yourself. Then we will solve it together. Well, I hope you were able to solve it. And if you weren't able to, that's absolutely no problem. We'll tackle the first question together and solve it. Look, we have 3 tangent theta. We'll take the differential of both sides. What does dx become? It's 3 times the quantity of 1 plus tangent squared theta d theta. Now let's go and substitute. What's in the numerator? So for dx, you're going to substitute it with 3 times the quantity 1 plus tangent squared theta d theta. What is in the denominator? 9 plus x squared. What is x? It's 3 tangent theta. So x squared is 9 tangent squared theta. Now you tell me, what do? Excellent. We'll factor out a 9 from under the radical. That becomes 9 times 1 plus tangent squared theta. 1 plus tangent squared theta, we've seen this quite often, haven't we? So what was 1 plus tangent squared theta? It would be 1 divided by cosine squared theta. So it then became 9 divided by cosine squared theta, all underneath the radical sign. Now what exactly comes out from underneath the radical? It's 3 divided by cosine theta. What do we have in the numerator then? We have 3 multiplied by 1 plus tangent squared theta. And 1 plus tangent squared theta, as we've mentioned before, is equivalent to 1 divided by cosine squared theta. The numerator is 3 over cosine squared theta. The denominator is 3 over cosine theta. Simplifying this is quite elementary. We obtain the integral of d theta over cosine theta. What was d theta over cosine theta? What was 1 over cosine theta? Excellent. Secant theta. We arrived at the integral of secant theta. Remember, in the second part, I told you that this integral of secant theta is very useful. Try to memorize its answer. If not, it's perfectly fine if you don't remember it. I explained its calculation method in the previous section, but let's assume that we all remember it now. If you don't recall, you can always go back to your notes or simply replay the previous part to review it. I proved to you that the integral of secant theta is the natural logarithm of the secant of theta plus the tangent of theta. All right, we have now successfully derived the solution for this integral expression. Specifically, the natural logarithm of secant theta plus tangent theta. However, our current solution is expressed entirely in terms of theta, whereas the initial problem was originally presented in terms of x. Consequently, we absolutely need to convert theta back into the variable x. We had defined x as 3 tangent theta. So what did tangent theta become? It was x over 3. What was tangent theta? The opposite side over the adjacent side. So the opposite side is x. And adjacent side is going to be 3. I'm going to draw a right triangle now. The side that is opposite is x, and the adjacent side is 3. we'll use the Pythagorean theorem. It becomes the square root of x squared plus 9. Now, what exactly are we looking for? We are looking for secant theta. Secant theta, as I mentioned, is the reciprocal of cosine theta. What exactly does cosine theta mean? Well done. Adjacent over hypotenuse. Now, the reciprocal, hypotenuse over adjacent, yes, that's secant theta, square root of x squared plus 9, all over 3. This is secant theta. What else do I need? Tangent theta. Tangent theta became x over 3. So we conclude that the integral of dx over the square root of 9 plus x squared became ln of the square root of x squared plus 9 plus x, all divided by 3. Let's move on to a different model. Let's do a quick recap of the two models. What have we seen so far? Up until now, we've seen an expression like a squared minus x squared, where I said we substitute x with a sine theta. What else did we observe? We also saw a squared plus x squared. For that one, I said we'd be writing x as a tangent theta. Now, the third model we'll see together here involves integrals of x squared minus a squared. In the first one, I said a squared minus x squared. Here, I'm saying x squared minus a squared. If we see x squared minus a squared, we take x as a secant theta. This is the last one, so don't worry, but they solve some very interesting problems. Let's move on to an example. The integral of dx divided by the square root of x squared minus 4. This is in the form of x squared minus a squared. What do I take x as? I'll take x as 2 secant theta. Now we're going to differentiate both sides. Tell me, what was the differential or derivative of secant theta? Last session, you were supposed to memorize this formula. I truly hope you've done that. The derivative of secant theta, that's right, is secant theta tangent theta. So if we take x to be 2 times secant theta, dx equals 2 secant theta tangent theta d theta. Now let's go ahead and substitute it. For dx, we get 2 secant theta tangent theta d theta. And in the denominator, under the square root, x squared becomes 4 secant squared theta minus 4. Now let's move on to simplifying it. We had said secant squared theta means 1 plus tangent squared theta. It's multiplied by a factor of 4, so it becomes 4 plus 4 tangent squared theta minus 4. Naturally, the 4 and minus 4 cancel out. What remains? The square root of 4 tangent squared theta. What comes out from under the radical sign? 2 tangent theta. What did I have in the numerator? 2 secant theta tangent theta. So the tangent in the numerator cancels with the tangent in the denominator. Here we have the integral of secant theta. Now you might recall we encountered secant theta in our previous problem. The integral of secant theta was found to be the natural logarithm of secant theta plus tangent theta. So what comes next? Excellent. We need to convert theta back to x. Let's just see what we're doing. What did we assume this time? We had initially taken x as 2 secant theta. So secant theta is now equivalent to x over 2. What was secant again? Secant was the reciprocal of cosine theta. So our cosine theta has become 2 over x. Now, if the cosine is 2 over x, we need the third side. Cosine is the adjacent side divided by the hypotenuse, so 2 over x. The adjacent side is 2, the hypotenuse will be x. I'm going to write out the Pythagorean theorem. Do you see our triangle? We have the opposite side here, then there's the adjacent side, and of course the hypotenuse. So what exactly are we looking for? Secant theta and tangent theta? Secant theta, that was already obvious from the beginning. We need tangent theta now. What would tangent theta be then? The opposite side over the adjacent side. So our tangent theta has been found. So what would be the definitive final answer? The integral of dx over the square root of x squared minus 4, which we had found to be the natural logarithm of secant theta plus tangent theta, became equal to the natural logarithm of x over 2 plus the square root of x squared minus 4 over 2. All right, now we want to solve some miscellaneous problems. What does that mean? It means it's not clear what method you should use. I want you to think about each question thoroughly by yourself, and then we can come together to solve it. I urge you, please try to work through the steps on your own as much as possible, if you truly wish to learn. If you're just going to watch this like a movie without letting it truly impact you, then you might as well just quickly glance over it. But you really need to dedicate time to think, and then come to me to solve this question. The first problem, which is our first example, is the integral of the square root of x squared minus 9. Divided by x dx. I'll remind you what we were doing for this. I told you about 3 different types of trigonometric substitution. A squared minus x squared. That's the expression we'd substitute with sine theta. Exactly. For a squared plus x squared, we would use tangent theta. Very well done. And for x squared minus a squared, we use secant theta. So which one is this now? Perfect. For x squared minus a squared, I want all of you to go and solve this problem by using the substitution x equals 3 secant theta, and then return with successful results. If you've approached this task with patience, you've certainly written something like this. We've taken x to be equal to 3 secant theta. We're going to take the derivative, or more precisely, we'll find the differential. So dx becomes 3 secant theta tangent theta d theta. Now let's proceed to substitute these values and see what we obtain. X squared is 9 secant squared theta minus 9 times 3 secant theta tangent theta d theta. What is this? This is exactly dx. Perfect. What does the denominator have? An x. What was x? 3 secant theta. Well done, everyone. I see that everyone is saying this. Perfect. Now, for simplification, we have 3 secant theta. The numerator and denominator will simplify. We have 9 secant squared theta. Minus 9. We can factor out the number 9 from under the radical sign. What will be left inside the radical then? 1 plus tangent squared theta. With that minus 1, it simply cancels out, you see? Only 9 tangent squared theta is left. Wow. Which emerges from under the radical in a simplified form. What exactly is left for us to consider now? We have the integral of 3 tangent squared theta. The integral of tangent squared theta. I told you it would be included in other questions, you see? It came. The integral of tangent squared theta, I proved it to you before. I showed that it equals tangent x minus x, but now you know that variables can change. Here, x has become theta. So, the integral of tangent squared theta becomes tangent theta minus theta, and don't forget that coefficient of 3 in front. Alright, so the answer we have now is in terms of theta. But as is our usual practice, we need to express it back in terms of x. So let's go ahead and bring x back into the equation. What was the substitution we made earlier? We had x equals 3 secant theta. Alright, so if x is equal to 3 secant theta, therefore the cosine theta will be equal to 3 over x. Cosine theta is the adjacent side divided by the hypotenuse. So in this case, 3 is the adjacent side and x is the hypotenuse. Tangent theta is opposite over adjacent. You already know this. So everyone, our final answer turned out to be 3 tangent theta minus 3 theta. And we have already determined the tangent theta. What is theta anyway? Didn't our cosine theta become 3 over x, or wasn't our secant theta equal to x over 3? It makes no difference. We simply take the reciprocal. But what does that even mean? So we can substitute for theta itself. You see, when we have cosine theta equal to 3 over x, then theta can be expressed as the arc cosine of 3 over x, or alternatively as the arc secant of x over 3. Both of these expressions are mathematically correct. So our final answer is written in terms of arc secant. We wrote down 3 times the square root of x squared minus 9 over 3 minus 3 arc secant of x over 3 plus c. Let's move on to another exercise. Everyone, please begin solving this problem. The integral of dx over the square root of x squared plus 6x. I'll give you a hint for this. The rest is up to you. What should you do? Complete the square under the radical. Everyone knows how to complete the square. If you don't know, you should check your high school textbook. I'll be waiting for you right here. So go ahead, pause the video, and come back. If we use the method of completing the square here, under the radical sign, it becomes x plus 3 squared minus 9. Now, which specific model is this? It's the model of x squared minus a squared. Well, what should we do now? We're here to solve this question. We take x plus 3 and set it equal to 3 secant theta. So you see, it doesn't necessarily have to be just x. Here it became x plus 3. I substituted 3 secant theta for x plus 3. Now let's take the differential of both sides. The derivative of x plus 3 is 1, so its differential is just dx. This is equal to the derivative of 3 secant theta, as we've often repeated. That is 3 secant theta tangent theta d theta. So dx becomes 3 secant theta tangent theta d theta. Let's go ahead and substitute all of that in. So, we place our new dx in the numerator, which is 3 secant theta, tangent theta, d theta. And in the denominator, under the radical sign, instead of x plus 3, we substitute 3 secant theta. When we square it, it becomes 9 secant squared theta. Exactly. Minus 9, just like the previous problems. Now, what can I factor out from here? The number 9. Again, we factor it out under the radical sign. Secant squared theta minus 1, as we know, the secant squared theta is equal to 1 plus tangent squared theta. The ones cancel out and we're left with tangent squared theta. Now, what exactly comes out from underneath the square root? A 3 and a tangent theta. These simplify with the 3 and the tangent in the numerator. So what we're ultimately left with is just the integral of secant theta d theta. And we've already calculated the integral of secant theta countless times before. It became the natural logarithm of secant theta plus tangent theta. Once again, using that familiar right triangle, we'll determine the secant theta and tangent theta values. We had previously established secant theta as x plus 3 over 3. Therefore, cosine theta, which is its reciprocal, becomes 3 over x plus 3. Again, we use this to find the opposite, adjacent, and hypotenuse. Let's substitute this in. Tangent theta is the square root of x squared plus 6x, all divided by 3. With this very simple substitution, the final natural logarithm answer is easily obtained. Just look at the final answer, see its sheer elegance and how easily we were able to find the result of this complex integral. In other words, if you differentiate this final natural logarithm, you'll get right back to our original question. Okay, the integral of 4 dx over x squared plus 2x plus 17 all raised to the power of 2. Now that it's out of the radical, this is a new phase, a new exercise. Now, everyone starts solving. The main idea once more is completing the perfect square. I'm asking you, if you're not familiar with perfect squares, go and look them up. Don't tell me, oh, I'm already an engineering student or I'm in some specialized field. I'm already too cool for this. I completed the square. There's nothing to it. You're absolutely right. There is nothing to it. But if you don't remember it for any reason, go and take a look at your high school math book. Well, I hope you all have done what was needed. If you complete the square inside the parentheses, you will have x plus 1 squared plus 16, and all of it squared. Now, what type is this exactly? It's the form a squared plus x squared. So, what do we get then? We would typically set x equal to a tangent theta. However, in this specific problem, because we have x plus 1, I'm going to take x plus 1. We'll set it equal to 4 tangent theta. Now, do we all understand that it's time for us to find the differential? Exactly. Let's take the differential of both sides. The differential of x plus 1 is just dx. And on the other side, the derivative of 4 tangent theta becomes 4 times 1 plus tangent squared theta, d theta perfect. Now, we're going to proceed with the substitution. What do we have in the numerator? Well, the numerator of the original problem already has a 4, so we have 4 times dx. Now, instead of dx, I'm going to substitute 4 times 1 plus tangent squared theta, d theta. So you see, we have the original 4 times our new substitution. Okay, let's move to the denominator. In the denominator, I'll replace x plus 1 with 4 tangent theta. Since it's squared, it becomes 16 tangent squared theta plus the 16 right next to it, which we're very pleased with. We look at this and see, oh wow, they're all common coefficients. Okay, now we can factor out 16 from this. What will remain inside the parentheses? 16 multiplied by 1 plus tangent squared theta. And remember, the entire expression is raised to the power of 2. We can simplify one of those terms with the numerator 16 in the denominator. Inside the parentheses, it's squared. Be careful, one of them cancelled out and one remained. So, what remained in the denominator was 16 multiplied by 1 plus tangent squared theta. Now, 1 plus tangent squared theta, which is something we are very familiar with, becomes 1 over cosine squared theta. I then inverted the entire denominator and brought it up to the numerator. 1/16th integral of cosine squared theta. That got much simpler, didn't it? Now, let's get to the next part. I'm not sure if you already know how to integrate cosine squared theta, but in one of our future lessons, I'll talk entirely about trigonometric integrals. Since this is very small and simple, I'll tell you right here. The integral of cosine squared theta, we cannot integrate sines or cosines that have even powers, unless it's with the help of the golden formula. You remember its name? The golden formula. It was so important. That's why we call it golden. In the textbooks, this is known as the power reduction formula, but here we call it the golden formula. It says cosine squared theta equals 1 plus cosine 2 theta, all divided by 2. Now, with the 1/16th that was already there, it became 1/32nd of the integral of 1 plus cosine 2 theta. Now, are we ready to integrate? The integral of 1 becomes theta. Well done. Someone mentioned x, but no, x is only for when we have dx. This here is the theta, my friend. So the integral of 1 is theta. Excellent. Now, what is the integral of cosine 2 theta? 1/2 times the sine of 2 theta. So let's convert the thetas back to x. What did we take as tangent? We had taken x plus 1 as 4 tangent theta. So tangent theta becomes x plus 1 over 4. Now, what was the definition of tangent? Opposite over adjacent? Perfect. So the opposite side is x plus 1 and the adjacent side is 4. Well, if we construct our well-known right triangle, we can very easily determine the cosine of theta. And what we have, I've already written it down using the Pythagorean theorem. It's quite simple. If we substitute, we'll get cosine theta, 4 over the square root of x squared plus 2x plus 17. Sine is also obtained very easily. Well, sine can also be found. The opposite side divided by the hypotenuse. That's exactly what you get. And this is sine theta. How do we find theta? In my last question, I said when you have a variable, a factor like tangent theta. Now, if you want theta, you just move the tangent from this side to the other, but don't forget its inverse. I'll substitute it now. The answer was 1 over 32 for theta. I wrote tangent inverse, and for sine theta, and for cosine theta. I substituted the relationships I derived using the triangle. It's truly very enjoyable. A question that starts so small yields such a big answer. If you practice, you can very easily find these answers. Let's move on to the next example. We're making it more complicated, making it tougher, but you, with all your practice, have also become more skilled. All right, let's move on to the next one. We have dx over the square root of 5 minus x squared minus 4x to the power of 3. Everyone knows what the very first step is, don't they? I'm not going to tell you. I'll give you some time. You go ahead and solve the problem, then come back. All right, let's go and see what the solution to this problem is. I hope that most of you have already solved it. If you haven't solved it yet, I'll explain it once at the end. Just keep this in mind. Then try to solve it yourselves again. And then we'll move on to the next questions. All right, what did it become under the radical sign? Radical 9 minus x plus 2 squared. Which model is this? A squared minus x squared. What did we substitute it with? Sine. So we'll use that substitution. We take x plus 2 in parentheses as 3 sine theta. Now we differentiate both sides. As we agreed before, dx equals 3 cosine theta d theta. Now let's substitute. For the numerator, I'll put 3 cosine theta d theta in place of dx. Under the radical, it becomes radical 9 minus. If I write 3 sine theta instead of x plus 2, when it's squared, it becomes 9 sine squared. Again, we factor out under the radical. From what? Well done, we factor out a 9. That becomes 9 times. 1 minus sine squared, and 1 minus sine squared, as we know, is cosine squared. So it turns into 9 times cosine squared, all raised to the power of 3. I'm not dealing with the power of 3 just yet. The square root of 9 times cosine squared is simply 3 times cosine. Now we'll apply the power of 3 to that result. The denominator is 3 cosine theta to the power of 3. And the numerator is the 3 cosine theta. We simplify it. The denominator remains 3 cosine theta to the power of 2. Okay, now I've squared it, and it's 190 theta over cosine squared theta. We've calculated the integral of 1 over cosine squared many times together. The integral of 1 over cosine squared is tangent theta. There was a 1/9 factor behind it, so it became 1/9 tangent theta. So the integral's answer was 1/9 tangent theta. Now we will proceed to find theta expressed in terms of x. I'd like to remind you once again, it was sine theta x plus 2, all divided by 3 from our famous right triangle. The opposite side to the hypotenuse. The opposite side is x plus 2 and the hypotenuse is 3. So we can very easily find the tangent. In terms of x, the answer was 1/9 tangent theta. So the final answer is x plus 2 divided by 9 times the square root of 5 minus x squared minus 4x. Let's go and solve another example. Which standard form does the integral of dx over x times the square root of x squared minus 25 correspond to? Excellent. X squared minus I squared. What was the method we applied for x squared minus I squared? Then okay, we were taking x as a secant theta. Everyone, please go ahead and solve this problem now. We will return shortly and review the solution together. We've set x to be equal to 5 times the secant of theta. We won't wait for anything. We'll immediately take the differential. So dx becomes 5 secant theta, tangent theta d theta. Now let's substitute this into the numerator. 5 secant theta tangent theta, and in the denominator we have an x. Don't forget that instead of x, we'll be writing 5 secant theta. Under the radical, instead of x 5 secant theta squared becomes 25 secant squared minus 25. I factor out the 25 from it. It becomes secant squared minus 1. Secant squared was 1 plus tangent squared, where the ones cancel out. If you perform the simplification, almost everything cancels out. What remained was 1/5 d theta. In fact, we want to integrate 1/5 d theta. The integral of a constant would have a theta multiplied into it. The integral of 1/5 d theta becomes theta divided by 5, as we've mentioned in our previous exercises. When we want to obtain theta, we simply need to invert our initial variable. This means that x divided by 5 was secant theta. So theta then becomes arcsecant of x over 5, and there's also a 1/5 coefficient in front of it. So the final answer to this question is 1/5 arcsecant of x over 5. We'll pause here on this problem. Go ahead and solve it again yourself. Let's move on to the next question. So we have x cubed over the square root of 25 plus x squared. What do we observe here? It's in the form of a squared plus x squared. What did we say we should do in such a case? We use the tangent substitution method. X equals 5 tangent theta. Now, we're going to take the differential of both sides of this equation. Dx is 5 times 1 plus tangent squared theta d theta. Okay, let's substitute x. X cubed with x being 5 tangent theta is 125 tangent cubed theta. I substituted dx 5 times 1 plus tangent squared theta d theta. That's it for the numerator. Now let's go to the denominator. The square root of 25 plus 25 tangent squared. If you factor out 25, it becomes the square root of 25 times 1 plus tangent squared. 1 plus tangent squared is 1 over cosine squared. So 25 over cosine squared. The square root is 5 over cosine. Now we will proceed to carry out the necessary simplification. We've taken out the remaining 125 from the numerator as a constant factor. There was also a 5 in the numerator, which has been cancelled out by a 5 in the denominator. We've written the numerator as 1 plus tangent squared. It's 1 divided by cosine squared. And in the denominator, we have 1 divided by cosine. Now, as you might already know, the term 1 divided by cosine squared in the numerator can be simplified with the 1 divided by cosine term in the denominator. And our integral will then take this form: 125 times tangent cubed divided by cosine. We write tangent cubed as sine cubed over cosine cubed. And that means the denominator becomes cosine to the power of 4. Now, which model is this? Do you remember? A model that incorporated both sines and cosine. Both of them have the ability. I had already told you which one we needed to expand. Excellent. We wrote the odd power in the numerator as sine cubed. That's sine squared multiplied by sine. As I explained in our previous lesson, the sine squared term in the numerator transforms into 1 minus cosine squared. Therefore, in place of the sine squared in the numerator, I've written 1 minus cosine squared. And then we place sine theta d theta at the very end of this expression. All of that, of course, is over cosine to the 4th power. If we substitute u for cosine theta, meaning that right in the middle of a trigonometric substitution, we abruptly move to a standard substitution. If we set cosine theta as u, then du will be equal to negative sine theta d theta. So when we see sine theta d theta, we can substitute it with negative du. This essentially means that a negative sign will be factored out. Now, if I perform the substitution, what will I obtain? We have negative 125 times the integral. For the numerator, since we let cosine be u, that becomes 1 minus u squared. And the denominator stays as u to the power of 4 du. All right, everything is ready now. We just need to write u4 in the denominator as u to the power of negative 4. If you multiply u to the power of negative 4 into the numerator, the fraction cancels out and negative 125 remains. The integral becomes u to the power of negative 4 minus u to the power of negative 2. We add 1 to the exponent and then divide by that same new exponent. This question has become quite a head scratcher. Its solution just doesn't seem to end. All right, so what happens next? The expression was obtained in terms of u. We substituted u with cosine theta. So it became negative 125 times 1 over the integrated terms. I replaced u with cosine theta. Cosine theta must then transform from this, and what does it become? It becomes x. But to do that, we need to look at our reference triangle. Tangent theta was x over 5, meaning opposite over adjacent is x over 5. So the opposite is x and the adjacent is 5. Using Pythagoras' theorem, the hypotenuse is the square root of 25 plus x squared. We'll find its cosine, which is 5 over that root, and substitute it. That was indeed a very captivating and deeply insightful question. You absolutely must work through several examples like this if you truly intend to reach a high level of proficiency and mastery. I know it was quite a challenging question. All right, for our next example, we're going to work through another multi-step problem together right here. You'll start this, you solve it, and then I'll give my final judgment, the integral of the square root of x squared plus 9 over x squared dx. As you can see, we again have x squared plus a squared. For x squared plus a squared, we'll use the tangent substitution. Everyone, go substitute x with 3 tangent theta, then we'll come back and solve it together. Okay, if you've done what I told you, meaning you wrote x as 3 tangent theta, and then you differentiated both sides. Dx is equal to 3 times the quantity, 1 plus tangent squared theta d theta. Let's go ahead and substitute that in. The radical x squared plus 9, which means 9 tangent squared plus 9. In the numerator, we have a dx. Instead of dx, I wrote 3 times 1 plus tangent squared. Excellent. We have a denominator, again, an x squared, which is 9 tangent squared. Now, you must have factored out a 9 from under the radical, making it 9 times 1 plus tangent squared. Or 1 plus tangent squared is equal to 1 over cosine squared. Now, inside the radical, we essentially have 9 over cosine squared. When we take it out, it becomes 3 over cosine theta. So, in the numerator, we have that 3 over cosine theta multiplied by the 3 from our dx. And since we are consistently writing all instances of 1 plus tangent squared as 1 over cosine squared, we'll apply the same rule to the dx part as well. So, this 1 plus tangent squared, I'm also writing it as 1 over cosine squared. Excellent. Next, we have 9 tangent squared. And we can see that they are all being expressed in terms of cosine. So I will write down the tangent squared as sine squared over cosine squared. We're starting now. We'll cancel out whatever we can. I'm referring to the expression. Naturally, we can cancel out any common terms between the numerator and the denominator. The cosine squared terms cancel out. 3 times 3 is 9. So the 9 in the numerator cancels with the 9 in the denominator. The numerator is completely cleared out, leaving just a 1. What remains in the denominator? It stays right there. We have cosine theta multiplied by sine squared theta. That comprises our entire mathematical expression. Now that the expression is somewhat simplified, let's proceed and see if we can integrate it. All right, let's review. You see, in the denominator, we had sine squared theta, meaning we have 1 over sine squared. As you recall, that equals 1 plus cotangent squared. So I'm going to take this 1 over sine squared and replace it. I'll substitute it with 1 plus cotangent squared. Why? You'll see in a second. All right, so in the numerator, I have 1 plus cotangent squared, and in the denominator, I have cosine. Now, I'm going to separate this into 2 fractions. 1 plus cotangent squared over cosine gives us 1 over cosine. What is 1 over cosine? Secant? Yes. Plus, I'll rewrite the cotangent squared as cosine squared over sine squared. One of the cosines cancels with the denominator. Okay, to keep things clear, I'll calculate these parts separately. I'll label the second integral as A, and I'll solve this specific one in just a single line. And the other part will be B. Then I'll simply combine them. This is turning into quite a challenging problem, but by approaching it this way, we'll gradually feel like we are tackling much more advanced integrals. All right, for A, we've encountered the integral of secant quite frequently. You see, I've told you repeatedly that performing integration truly demands experience. As your practical experience gradually increases, you've solved the integral of secant so many times that by now you can effortlessly tell me what its result is. The integral of secant is the natural log of secant plus tangent. So I've already taken care of the first integral. Now let's move on to the second one, the integral of cosine theta divided by sine squared theta. How should I go about solving this one? Which specific model is this referring to? It's enough to just take the sine of theta as u. If we take sine theta and assign it as u, then we get cosine theta d theta as du. It becomes the integral of du over u squared. This is easy for us. U squared becomes u to the power of negative 2, add 1 to the exponent, then divide by the new exponent, which gives negative 1 over u plus c. I'll substitute u with sine theta. So the first integral became the natural log of secant plus tangent. The second one turned out to be negative 1 over sine theta. These two expressions must now be added together. Our integral's final result is now expressed in terms of theta. We want to eliminate theta. We've eliminated theta so many times. I know it no longer holds that initial fear for you. We had taken tangent theta as x over 3. So the opposite side is x and the adjacent side is 3. I'll find the hypotenuse using the Pythagorean theorem. So secant is the reciprocal of the cosine. This means that instead of adjacent over hypotenuse, it becomes hypotenuse over adjacent. You can see we've written it right there. Plus tangent theta, which I had taken as x over 3. So plus x over 3, that's very good. Minus 1 over sine, and sine, as we know, is opposite over hypotenuse. But since this is its reciprocal, it becomes hypotenuse over opposite. What exactly have I been explaining to you up to this point regarding trigonometric substitution? I've introduced and taught you 3 fundamental relationships. For each of these 3, I've worked through a vast number of examples. I can practically guarantee that any trigonometric substitution problem you encounter will fall into one of these specific models that I've thoroughly explained to you. There's just one more creative model, and it would be a pity not to mention it after everything we've covered regarding trigonometric substitution. I'll share this one with you too, so we can finally close the chapter on trigonometric substitution. This is the last model, and we're going to see. It involves calculating the integral of functions that appear as a fraction with the numerator being 1. Now, if there's a numerical coefficient, we simply take that number outside the integral. That's not important. In the denominator, you'll find a multiple of sine plus a multiple of cosine plus some constant number. We'll also examine this model. It implies that it might only involve sine or cosine. You can solve that type using this method as well. All right. So what exactly is the method? We are going to set t equal to the tangent of x over 2. Before I go any further, let me quickly remind you of a key trigonometry formula. After that, we'll go through a couple of examples to really master it. We had a formula in trigonometry specifically for expressing sine in terms of tangent and cosine in terms of tangent. Let's look at the relationship together. Sine x equals 2 tangent x over 2 divided by 1 plus tangent squared x over 2. We have a similar formula for cosine as well. The cosine of x is equal to 1 minus the tangent squared of x over 2, all divided by 1 plus the tangent squared of x over 2. Be mindful that whatever the angle for sine or cosine is, the angle for the tangent will always be halved. And tangent x itself can also be written in terms of the half angle. Tangent x is also equal to 2 times tangent x over 2, divided by 1 minus tangent x over 2. You do not need to write this down. I have already included it for you in your notes. Just focus your attention and observe how I am going to utilize this. Let us proceed and examine the example together now. First, let us look at a very small example. I gave you the integral of dx over 4 plus 2 sine x. I see the numerator is a constant, which is good. The denominator is a first degree expression in terms of sine, cosine, or both. We can use this method for these types of problems. Although we might be able to solve them using other approaches, this method is extremely powerful. What does that mean? It means it can handle most problems of this kind. Watch what I do. I am going to introduce a new definition here. We will say that t is equal to the tangent of x over 2. This specific relationship where t is defined as the tangent of x over 2 is what we call a new substitution of variables. All right, if this situation occurs according to our earlier agreement, what was the very first thing we had to do after making the change of variables? Bravo, differential. Let us not waste time. We will quickly find the differential. What do we get? dt equals 1/2 times 1 plus tangent squared of x over 2 times dx. Now, we had set the tangent of x over 2 as t. So now, in dt, which is 1/2 times 1 plus tangent squared, what can I put in place of tangent squared again? E. So dt equals 1 plus t squared times 1/2 dx, or equivalently dx equals 2 over 1 plus t squared dt. Now, so I have successfully determined dx as a function of t squared. Now, our next step is to express the integral completely in terms of t. Let us take another look at the problem statement. In the problem statement, we have dx. Okay, I have dx expressed in terms of t. Here, I am quite comfortable with the denominator, which is 4 plus 2 sine x. What was it that we took as t? I substituted the tangent of x over 2 as t. What did sine have to do with the tangent of x over 2? It is the same formula I told you about. It was the sine function. 2 times the tangent of x over 2 divided by 1 plus the tangent squared of x over 2. What did I call the tangent of x over 2? T. That is very good. So the numerator became 2t. My denominator ended up being 1 plus t squared. See, I am trying to do something here. I want to make sure there is no trace of x left so we do not get lost in the middle of solving these problems. All right, let us proceed now. My friends, we will substitute once more. We have found the expression for dx in terms of dt, which is 2 dt divided by 1 plus t squared. I have found the sine function below, expressed in terms of t. Now I want to put these in their place. Let us see what it looks like. It might appear a little bit messy or awkward at first, but it is actually quite easy to solve. The numerator is expressed in terms of t, and the denominator is also in terms of t. As you can clearly see, I have two options here. Either multiply both the numerator and the denominator by 1 plus t squared to make the expression a bit more compact and manageable. You can either find a common denominator or multiply outer by outer and inner by inner. The first approach is a little more sophisticated. As a good student, try to avoid skipping the common denominator and immediately going to outer by outer and inner by inner. That particular method is somewhat unsophisticated. Just multiply the numerator and the denominator by the denominator's LCM. Now, since the denominators are the same here, you can very easily multiply the numerator and the denominator by 1 plus t squared, and it becomes very neat. We have a 2, and I have factored out a quarter from the denominator. Do not ask what that 4 is. I have factored out a quarter from the denominator and taken it outside. There was also a 2 in the numerator, which I have also taken outside. So what was left in the numerator is dt over t squared plus t plus 1. You can see there is absolutely no sign of any sine function here. The trigonometry has vanished completely and turned into an algebraic expression. What am I going to do now? The very thing we have tried to practice so many times. What is it? A perfect square. If you can make the denominator a perfect square, and I really hope you have been able to accomplish that, as 2/4 with the outer coefficient in the denominator, dt over 3/4 plus the quantity t plus 1/2 squared appears. It is starting to look like arctangent. Excellent. A squared plus some expression squared, arctangent. Well, what I actually did was this. I wrote down the 3/4 as the square root of 3 over 2, all raised to the power of 2. t plus 1/2, all squared. Are you ready for the final part? Let us move on to the very last step. Now, according to the formula we previously established, let me remind you one more time. The integral of dx over a squared plus x squared would be 1 over a arctangent x over a. Now, nothing has happened. X has been replaced by t plus 1/2. So 2/4 remains outside. A is root 3 over 2. I mentioned 1 over a, meaning the inverse of a, so it becomes 2 over root 3. You see, this is multiplied by arctangent. X was replaced by t plus 1/2. And a is root 3 over 2. Now, what was t? You have not forgotten we had a term for this problem. What was t? The tangent of x over 2. Instead of t, I also put the tangent of x over 2. It also has a very stylish and classy appearance. When you see the answer to this question, you should really write this down on your paper. I believe your professor will certainly have even more respect for you. That was indeed a very profound and excellent question. Bravo! Now let us proceed to the final question. This is going to be the section, the integral of gx, where I have included both sine and cosine terms. You see the numerator is 1, and the denominator is a first-degree expression in terms of sine and cosine. What should we do in this case? We decided to set t as the tangent of x over 2, and then immediately differentiate it. I am not continuing. You stop right here. This is the last question of this section. You go and solve it, then you come back. I know the last question is quite a tough one. I want everyone to think about it. Look at the previous one. What did I do? Solve as much of it as you can yourself. Go and come back. You all did a great job. Bravo to everyone who solved it. Bravo to everyone who thought about it. Even if you could not solve it, I am certain that reviewing what I have told you will surely increase your odds. Let us look at the solution to the final question together. We set t as the tangent of x over 2. We differentiated both sides. dt became 1/2 times 1 plus the tangent squared of x over 2 times dx. Everyone is with me so far. I am not losing anyone. What I'm trying to do is take dx and put dt in its place. So the first step is to isolate dx. If you clearly understand what your objective is, you will not lose your way. I am looking for x to become extinct. X should go and t should remain. So now that we have reached this point, just isolate dx, know what you are doing. This becomes 2 dt divided by 1 plus t squared. Now, for every instance of x, I will substitute t. So the numerator is now completely ready. dx becomes 2 dt over 1 plus t squared, which I will throw into the numerator. Now for the denominator. What do we have in the denominator? We learned about sine x. Sine x becomes 2 times the tangent of x over 2 divided by 1 plus the tangent squared of x over 2. Since I took the tangent of x over 2 as t, I just wrote 2t for you. And below, I had mentioned it is plus tangent squared, meaning 1 plus t squared. My denominator for the cosine function is exactly the same. This means that for cosine as well, the denominator is 1 plus t squared, only its numerator is 1 minus t squared. Now I will take sine and cosine and substitute them with the t's. Why? Because x is going to be eliminated. We absolutely must not have x. We are in the process of replacing it with t. The sine was removed, the cosine was removed. What came in their place, you might wonder? Algebraic expressions in t. All right, so I have gone ahead and written the sine and cosine in terms of t. It might have a rather unpleasant or awkward appearance. It has been observed. Students, meaning they just gave up right here, saying, well, forget it, we have worked hard enough. Then they congratulated themselves and stepped aside. But believe me, there is not much left. It is easy if we look now. We have a 1 plus t squared behind the parentheses. If you multiply by each factor, 1 plus t squared cancels out. What is more beautiful than this? It fits together so well, and it always happens this way. This means that this is a change of variable. The clever part is that they are arranged together in such a way that they all simplify completely. So what happens if I actually perform this simplification? The numerator was 2 dt. The entire fraction was eliminated. In fact, the whole denominator was cancelled out. What remained after simplification was 2 dt in the numerator, and in the denominator, negative t squared plus 2t plus 3. Alright, so here I am going to make use of a specific lemma, which I will be teaching in very extensive detail in the next upcoming section. What I mean is that I deliberately included a particular element in the final question, precisely so I could explain this concept to you in the subsequent part. I am just going to mention it briefly here, simply because this specific model is quite a straightforward one. But rest assured, you will definitely see a much more complex and heavier version of it in the later sections. For the denominator, there are two distinct operations you can perform. One of these is completing the square. You can also use the method that is being applied here. Since I want this to be an exercise for our next session, I will use this approach. What exactly do? I will factorize the denominator. I factor out a negative from the denominator and move it to the numerator. Then I factor the denominator. Does everyone remember factoring? I am going to decompose this. The numerator is negative 2 dt, and the denominator is t plus 1 times t minus 3. Look, there is a partial fraction decomposition method. It states that it becomes 1 over the smaller factor minus 1 over the larger factor. This is a very quick method for decomposing the product of two linear terms. Pay attention. Multiplying two first-degree monomials. What do? I say it becomes 1 divided by the smaller term. Okay, in this case, the larger factor is t plus 1, and the smaller factor is t minus 3. So it becomes 1 over t minus 3 minus 1 over t plus 1. What is their difference? Negative 3 and 1, 4. I will take the reciprocal of that. Let me explain it again. It is a very quick method. I'm talking about 1 divided by the smaller factor minus 1 divided by the larger factor. What is the difference between the expressions t minus 3 and t plus 1? 4. So we take the reciprocal, 1/4, and place it outside as a coefficient. What is remaining now? The difference between two fractions whose denominator is a first-degree polynomial. I recall mentioning in our previous discussions that for any fraction where the denominator is a first-degree polynomial, its integral will always result in a natural logarithm. Therefore, the integral of dt divided by t minus 3 becomes the natural logarithm of t minus 3, and the integral of dt divided by t plus 1 becomes the natural logarithm of t plus 1. Alright, this section is now complete. This was a part that had a lot of new material. It contained many trigonometric formulas, but with more practice, by practicing similar tests found in other books, whether foreign references or domestic ones, you will become much more comfortable with it. If you solve these examples, you will certainly become proficient. There is absolutely no reason to be scared. The real horror is reaching higher levels in academia or in our careers and then being unable to do our basic engineering calculations. I hope that with more practice, I will see you much more proficient next time and we will explore other new things together. Do not forget, math is all you need.